In this video, I'm going to show you how to deal with generalized eigenvectors. Now, when solving a system of differential equations with a repeated eigenvalue like this one, sometimes you only find one eigenvector, and you can use that one eigenvector along with a Jordan cycle to generate the other eigenvectors you need. Now, in this situation, I'm going to get more than one eigenvector on my first pass, so I can't use a Jordan cycle to get those next eigenvectors. What I've gone ahead and done is plugged in lambda equals -1 into this lambda subtracted matrix, and now I need to row reduce. What I'm going to do is swap this third row into the first row and multiply it by -1 while I'm at it. So I have -1, -1, 1, 1. That's going to become 1, 1, -1, -1, augmented with a column of zeros. And I'm also going to say this third row is now 0, 0, 2, 0. I'm going to use this 1 to get zeros down below. So 2 times 1 is 2, added to -2 is 0. I get 0 here. 2 times -1 is -2, added to 1 is -1. And I'm going to get a 0 here. I'm also going to add 1 times this row to this last row to give me 0, 0, 1, 0. Now that I have a -1 here, I'm going to multiply this second row by -1 to give me 1, 1, -1, -1. Now that I have a 1 here, I'm going to use this 1 to get zeros below. -2 times 1 is -2, added to 2 is 0. Same thing, -1 times 1 is -1, added to 1 is 0 here. I'm going to use this 1 to make a 0 above. So I'm going to add this row to the top row, and that's going to give me a 0 here instead. Okay, this is the row-reduced form, a row-reduced echelon form of my matrix. This is a pivot column here. Let's go ahead and find our pivot and free variables. This is a free variable. This is a pivot. This is a free variable, so I have pivot free, pivot free. Let's go ahead and write this first equation as x1 plus x2 minus x4 equals 0. And this second row here just reads x3 equals 0. Okay, here I have two free variables, namely x2 and x4. Let's go ahead and let x2 equal 1 while letting x4 equal 0. This is going to generate one eigenvector. Or I could let x2 equal 0 while letting x4 equal 1. When this happens, I get the possible values for x1. Letting x2 equal 1 here and x4 equal 0, I get x1 equals -1. x3 is always going to be 0, so I'm going to go and fill that in for both eigenvectors. And in this situation, when I let x4 equal 1 and plug it back into this first equation, again letting x2 equal 0, I get x1 equals 1. Now these are my two eigenvectors on my first pass through. Notice I can't do a Jordan cycle because I don't get just one eigenvector. What I need to do first though is create the linear combination of this eigenvector with this eigenvector using alpha and beta. So what I'm going to say is alpha times this vector plus beta times this vector. I'm going to say alpha times -1, 1, 0, 0 plus beta times 1, 0, 0, 1. And you know what? I want to write this as one vector. So I'm going to combine these into one vector, giving me negative alpha plus beta, alpha, 0, and beta. Okay, now that I have this eigenvector in terms of alpha and beta, what I want to do is I want to take this guy and substitute it into this original lambda subtracted matrix, augmenting not with a column of zeros, but with this eigenvector as a column. So I'm going to erase these zeros and replace it with negative alpha plus beta, alpha, 0, and beta. And I want to row reduce on this guy just like I did on this, but now that I have a column of alphas and betas instead of a column of zeros. So here I go. Once again, I'm going to change this -1 to a +1, but that in turn changes my alpha to a negative alpha here. I'm going to use this 1 now to get zeros below, so -2 times 1 is -2, added to this is going to give me 0, but now I'm going to have alpha plus beta, since -2 times negative alpha is 2 alpha, added to negative alpha is just positive alpha. Same thing again, -1 times -1 times 1 is -1, added to 1 is 0. But then I have -1 times negative alpha is alpha, added to beta gives me alpha plus beta. And lastly, I'm going to add this row, this 0, 0, 1, to the top row, giving me 1, 1, 0, -1, negative alpha. And this middle row, or the second row, doesn't change. Okay. Now that I have this matrix, I want to point out we've got a couple rows that equal alpha plus beta, some expression of alpha and beta. With that in mind, I want to set these two expressions here equal to 0. I want this row of zeros to equal 0. So I'm going to say alpha plus beta equals 0 and alpha plus beta equals 0. Now I know that seems redundant, but I want to write it as a matrix, so it's important that I write both equations. Here I have 1 alpha plus 1 beta equals 0, and 1 alpha plus 1 beta also equals 0. I can row reduce this guy, subtracting the first row from the second to give me 1, 1, 0, 0, 0, 0. Just like always, I'm going to go ahead and label this my pivot column, and this will be my free variable. I'm going to let my free variable equal 1, so that means beta equals 1 here. And if beta equals 1, plugging it back into this equation, I find that alpha equals negative 1. Okay, now that I have alpha equals negative 1 and beta equals 1, I'm going to substitute these two guys into this matrix back in here, replacing alpha by negative 1 and beta by positive 1. So here I go. Okay, notice that by plugging in alpha equals negative 1 and beta equals 1 into these two expressions here, they become 0. And I have just another system of equations where I have a pivot, a free, a pivot, and a free. This is my two pivots here. Normally, I let my free variables each equal 1, but because I have a non-homogeneous system, I can actually let my free variables equal 0 in this situation. I'm going to go ahead and let x2 equal 0 and x4 equal 0. And this equation reads x1 plus x2 minus x4 equals 1, and this equation reads just that x3 equals 1. So I got x3 equals 1. I said, x2 and x4, they're free variables, but this time I can let them equal 0, and if they do equal 0, I can say x1 equals 1. So I now have this new eigenvector here, 1, 0, 1, 0. What I'm going to do with this eigenvector, I'm going to hold off for a second. In fact, I'm just going to call this eigenvector, I call this eigenvector the baby. It's kind of a weird name for it, but that's the baby eigenvector. I also need to find the dad eigenvector. The dad eigenvector I get by taking the value of alpha equals negative 1 and beta equals 1 and plugging it way back up here into where I got that linear combination of alpha and beta. Now when I do that, I get negative 1, which is 1 plus 1 is 2, negative 1, 0, and 1. And that gives me the dad eigenvector. So this is dad, this is the baby. To get your answer, your solution, I'm going to do this in pink here. The solution using this eigenvector and this eigenvector, just for the repeated eigenvector, is going to be C1 times e to the negative t times the baby eigenvector, that would be 1, 0, 1, 0, plus t times the dad eigenvector. That was 2, negative 1, 0, 1. That is the long, arduous process of doing a generalized eigenvector in the case where we have a non-zero expression over here on the right. That is to say, sometimes we get 0 over here, but in this case, we got some alphas and betas. The process will be totally different when I get 0 over here. Here we have another 4x4 matrix for which we need to find generalized eigenvectors, because when I go and find the eigenvalues for my first pass, I'm going to get more than one, so I can't do a Jordan cycle. But something different is going to happen this time. I'm going to go ahead and do my row reduction real quick. Let's go ahead. This looks an awful lot like the row reduced echelon form from the previous example we did, where I have a pivot here, a free variable here, a pivot here, and a free variable here. With that in mind, I'm going to go ahead and write this equation, x1 plus x2 minus x4 equals 0. And this row just reads again, x3 equals 0. I once again have two free variables, x2 and x4. So I'm going to let the two possibilities go forth and take place. x2 could equal 1 while x4 equals 0, or x2 could equal 0 while x4 equals 1. x3 equals 0 in both cases. We already found that. And when x2 is 1 while x4 is 0, I find that x1 is negative 1, and I find that x1 equals 1 in the case where x4 is 1. Okay, I have my two eigenvectors again, but I'm going to do it one more time. Alpha times this eigenvector plus beta times this eigenvector. So I'm going to say alpha times negative 1, 1, 0, 0 plus beta times 1, 0, 0, 1. This is going to give me a combined vector of negative alpha plus beta, alpha, 0, beta. Okay, once I have this combined linear combination in terms of alpha and beta, I'm going to replace it into this vector over here. Instead of augmenting with a column of zeros, I'm going to augment with a column of alphas and betas. Okay, I want to notice that now that my row reduction is complete, I have these rows of 0 equal 0. They don't equal expressions of alpha and beta like they did before. And so with that in mind, both alpha and beta are free. In one instance, I'm going to let alpha equal 1 while I let beta equal 0. And in another instance, I'm going to let alpha equal 0 while I let beta equal 1. Let's start with the case where alpha equals 1 and beta equals 0. When I plug alpha equals 1 and beta equals 0 into this matrix, I get the following matrix. Now I want to go ahead and find my pivot columns and my free variables. This is a pivot column, this is a free variable, this is a pivot column, and this is a free variable. Again, because I have a non-homogeneous system here, though I've got a non-zeros on the right-hand side, I can let my free variables equal 0. I'm going to say x2 equals 0 and x4 equals 0. And then x1 is going to equal negative 2/3, while x3 equals negative 1/3. This is the baby eigenvector. This is baby. And in order to get the dad eigenvector, I'm going to go back and take alpha equals 1 and beta equals 0 and plug it into this guy. So the first dad eigenvector is negative 1, 1, 0, 0. This is the case where I have alpha equals 1 and beta equals 0. So the solution I will get is as follows. I'm going to get C1 times, or C1e to the negative t times the baby eigenvector of negative 2/3, 0, negative 1/3, 0, plus t times the dad eigenvector. That was negative 1, 1, 0, 0. But now there's another solution. That corresponds to when alpha equals 0 and beta equals 1. So I'm going to redo this process, taking alpha equals 0 and beta equals 1, plugging it into this matrix and seeing what I get. Once more, this is a pivot, this is a free variable, this is a pivot, this is a free variable, and again, because I have a non-homogeneous system that I'm dealing with, my free variables of x2 and x4 can be 0. So that's 0, this x4 can be 0, and then with this in mind, x1 has to be 1/3, and x3 has to be 2/3. This is the baby eigenvector for alpha equals 0, beta equals 1 case, and to get the dad eigenvector, I take alpha equals 0 and beta equals 1, plugging it back up here. I'll get the new dad eigenvector of 1, 0, 0, 1. So the solution generated by this system, or this situation, will be C2 e to the negative t times the baby eigenvector of 1/3, 0, 2/3, 0, plus t times 1, 0, 0, 1. And these are the two solutions generated when this case happens. I want to point out that the key difference between this problem and the last was that I got equals 0 on the right-hand side of this augmented matrix. I didn't end up with an expression of alpha and beta, and with that in mind, I had two possibilities, that alpha was 1 while beta was 0, or that alpha equals 0 while beta equals 1. In this last example, my first pass to find eigenvectors is going to generate 3 eigenvectors. Watch what happens when I row reduce this lambda subtractive matrix. I'm going to go ahead and swap the second row into the first, giving me 1, 1, negative 1, negative 1, zeros here, and zeros down below. And then I can use this 1, 1, negative 1, negative 1, multiply it by 3 and add it to this, giving me zeros here, and giving me zeros on the third row. Now, I have one pivot, while the rest are free. So with that in mind, I have the equation x1 plus x2 minus x3 minus x4 equals 0. I could let x2 equal 1 while letting x3 and x4 equal 0. I could let x2 equal 0 while letting x3 equal 1 and x4 equal 0. And I could let x2 and x3 be 0 while letting x4 equal 1. When I solve for x1 in each of these situations, I find x1 is negative 1, x1 is 1 here, and then x1 is 1 here. So these are my 3 eigenvectors, negative 1, 1, 0, 0, 1, 0, 1, 0, and 1, 0, 0, 1. So I have my first 3 eigenvectors. Now what I want to do is write a linear combination of these 3 eigenvectors using alpha, beta, and because I have a third eigenvector, gamma. So I'm going to say alpha times negative 1, 1, 0, 0, plus beta times 1, 0, 1, 0, plus gamma times 1, 0, 0, 1. And of course, I want to write this as one vector. So I'm going to write this as negative alpha plus beta plus gamma, alpha, beta, gamma. Now that I have this vector, I want to augment my original lambda subtractive matrix by, not by zeros, but by this vector here. So I'm going to go ahead and erase this and replace it with this vector. Now that I've gone to replace this this last column, this augmented column, by this vector over here, I'm going to row reduce once again. I've gone ahead and swapped this second row with the first row once again, putting the negative alpha plus beta plus gamma here and putting the alpha here. I'm going to use this row here to make zeros here and here. 3 times this row added to this row is going to give me 0, 0, 0, 0. 3 times alpha is 3 alpha added to this negative alpha is 2 alpha. Plus beta plus gamma, and 2 times this row added to this row is going to give me 0, 0, 0, 0, and I'm going to get 2 alpha plus beta here, and this bottom row is still zeros with a gamma at the very end. The top row is 1, 1, negative 1, negative 1, and with an alpha at the very end. Now, just like the first example we did, we've got a row of zeros equaling some expression in terms of alpha, beta, and gamma. So I'm going to write these equations out. 2 alpha plus beta plus gamma equals 0. 2 alpha plus beta equals 0. And gamma equals 0. Now, this looks like a 3 by 3, and I could write it as a 3 by 3. But you know what? Gamma equals 0 causes this to go away, causes that to go away. So I once again just have this 2 by 2 system of 2 alpha plus beta equals 0 and 2 alpha plus beta equals 0. I'll write this in 2, 1, 0, 2, 1, 0. And if I do row reduction, to get row reduced echelon form, I get 1, 1 half, 0, 0, 0, 0. Letting beta equal 1, my free variable, once again, solving for alpha gives me that alpha equals negative 1 half. Okay, now that I have alpha equals negative 1 half and beta equals 1, I'm going to plug these back into this matrix up here. I'm going to replace alpha by negative 1, replace alpha and beta and gamma by their respective values. I'm going to get the following matrix. Now that I've replaced alpha, beta, and gamma by the values I found over here, I'm going to go ahead and find my pivot, which is this guy here, and the rest of these values are free variables. Again, I have a non-homogeneous system. This right-hand side is non-zero, so I can let all my free variables equal 0. So this is going to be x1 plus x2 minus x3 minus x4 equals negative 1 half. But like I said, I've got a non-homogeneous system. So I can let x2, x3, and x4, all of my free variables, all of these guys can equal 0. So I'm going to say x2 equals 0, x3 equals 0, and x4 equals 0. And when all these things are 0, I get x1 equals negative 1 half. This is what I call the baby eigenvector. And I need to find the dad eigenvector. Well, dad can be found by replacing alpha, beta, and gamma by the values I found a moment ago. So I have alpha equals negative 1 half, beta equals 1, and gamma equals 0. Plug them into this vector to get negative 1 half is 1 half, plus 1 is 3 halves. Alpha equals negative 1 half, beta equals 1, and gamma was equal to 0. So this is what I call the dad eigenvector. And so with that in mind, I've got baby, and I've got dad. I can get my solution, which looks like this. C1 e to the negative t times the baby eigenvector, negative 1 half, 0, 0, 0, plus t times the dad eigenvector. And that dad eigenvector was 3 halves, negative 1 half, 1, and 0. That is generalized eigenvectors, and we've shown you a few cases sometimes where, again, it boils down to what happens when I row reduce with the augmented matrix full of alpha, beta, and gamma. Notice that in this case, the row of zeros didn't equal 0. It equals some expression using alpha, beta, and gamma. So I had to put this into a matrix form, find the values of alpha and beta and gamma that caused this to all equal 0, and that generated my new solution.